Thank you for the introduction. Today, I'll talk about an adaptive sampling method and a reachability-based interpolation technique for fast and efficient sound propagation. Games and virtual reality applications require propagation effects to create believable virtual worlds. Sound propagation effects provide important perceptual cues that allow us to locate sound sources in a virtual environment. These oral cues are essential to provide the listener with an immersive experience in VR applications. We use precomputed systems to perform the expensive transport simulation offline at a sample set of probe locations. Here, the blue boxes represent the probe locations. At runtime, the acoustic parameters from these probes are interpolated to the player location. Here is a demo of one such system. Notice sudden abrupt loudness changes because of missing probes. Precomputed systems often use uniform sampling of probes and visibility-based interpolation techniques. We discuss a few issues with these approaches. Uniform sampling often misses probes in narrow regions. For example, here on the right side, we see a red dot, which indicates a potential player location, and there are no probes available at this point. We must increase the sampling density to sample such narrow regions. However, this is not practical due to the memory and computation requirements. At runtime, precomputed probe information must be interpolated to the player location. Probes that are invisible to the player are often rejected, which introduces audible jumps. Human auditory perception is sensitive to such loudness changes on slight player motion, breaking immersion experience in VR. We address these two issues with our adaptive sampling approach. Here is a demo of our system. Now we have a smoother transition because we have more probes available in this narrow region. We would like to emphasize that we do not use more probes, but rather place them better when compared to the uniform sampling case. We use a scene voxelization to compute the geometric intersection and scattering required for our adaptive sampling approach. We use the same setup for simulating wave acoustics, but other implementations are also possible. We pre-compute numerical wave simulations. Here is a simple illustration for the Citadel scene. We visualize a 2D slice of the simulation. A and B are two listener locations. We start a pulse source at a point. Sound waves bounce, diffract around geometries before entering the cathedral. They reach listener point A first, and then listener point B, diffracting across the castle walls. The impulse response records these sound wave interactions between the source and listener. Acoustic precomputation is a 7-dimensional problem, as both source and listener can move in 3D, and it also includes a time-dependent impulse response results for each pair. We built upon prior work based on parametric encoding and briefly describe it here. The impulse response can be categorized into 3 transient stages: direct sound, early reflections, and late reverberations. Direct sound captures the initial arrival of sound waves that contain high energy contributions. Early refractions represent sound waves that reflect, diffract, scatter around geometries before arriving at the listener. And late reverberation represents sound waves that have bounced off many times off the geometries and often arrive simultaneously with parameters, which cover a wide range of acoustic effects. We include two loudness parameters, direct and reflected energy, and two decay rate parameters, early reflections and late reverberations. Please refer to the paper for more details. We have three main components in our system, and we give a brief description. And we achieve smooth acoustic effects through a runtime interpolation technique based on radial weights using geodesic shortest path lengths. We'll describe each one of these steps in detail now. Local diameter captures a notion of scene's local spaciousness or narrowness around a given point. We use this measure to adapt the probe density, a path directness function. This allows us to vary weights smoothly as energy flows from a probe to the player, thus attenuating sounds rather than cutting out abruptly at visibility transitions. Our reachability-based interpolation technique ensures smoothness, for example, as the player moves from position A to position B, lowering the weights accordingly. We'll look at some results now and listen to a few of them. We visualize the reconstructions such as Citadel. Uniform sampling can often miss such regions as shown in this case. Our technique adapts resolution locally to guarantee sampling within such thin, narrow features. We presented a system to capture acoustics for narrow features within a practical budget for precomputation and runtime memory. Our work has been integrated into Triton and has been shipped in games and virtual reality applications. Thank you.
Nice work, Dinesh Mehrotra, Maryland. Will this activity apply to dynamic scenes if you have a door opening and closing? A lot of sound field changes because of that.
Right now, dynamic scenes are not supported. So we have dynamic sources and dynamic listeners and static scenes. So this could be something to look into the future. Thank you.